In 1783, an English clergyman named John Michell, and completely independently by the eminent French scientist Pierre-Simon Laplace, came up with the concept of a dark star that could be so enormous, in Michell's case calculated at least 500 times the mass of the Sun, where it simply had too much gravitational pull for light to escape. It was a very simple calculation. At what point does escape velocity exceed the speed of light? Perhaps surprisingly, they knew the speed of light back then, and had known since 1676 in observations done by Danish astronomer Ole Romer regarding the eclipses of Jupiter's moon Io. And of course they knew how gravity behaved, thanks to Newton. These scientists were both missing a piece of the puzzle: degeneracy pressures. They didn't know about that, where the components of the atom push back and hold up against gravity until it reaches a point of no return. The pressures are overcome and everything collapses. And instead of a giant dark star resulting, a still every bit as massive singularity of some type forms that is quite small, hidden in an event horizon. We know these today as black holes. But the story turned out far more complicated than those early theorists could have imagined. The best they could do at the time was realize that physics forces the reality that gravity can prevent light from escaping. The idea generally just sat there, mostly forgotten for most of the 19th century. But the opening years of the 20th century saw the advent of Einstein's general relativity. And one glaring prediction of that framework is our modern view of black holes. In 1916, Carl Schwarzschild did the math for black holes based on general relativity. And by 1964, an experiment involving sounding rockets picked up an X-ray source in the constellation of Cygnus, then dubbed Cygnus X1. By 1967, John Archibald Wheeler had coined the phrase black hole. And in 1971, an unseen massive object was independently detected apart from its X-rays to be wielding gravitational influence in the Cygnus X1 system. It seemed at that point that this was a rock-solid candidate for a black hole in nature. And in subsequent years, more evidence was found sufficiently to declare it the first black hole ever discovered. Now, they are routinely spotted, and using a trick of radio astronomy, interferometry, and computers, something close to an image of a black hole nested in its accretion disk was taken. This has happened several times since, and while not a real picture per se, it is an image, and is taken from data, and maybe the closest we will ever get to seeing one of the universe's greatest monsters. Or maybe not. And one of the things we have found out regarding black holes is that they need not be monsters at all. More on that in a bit. But black holes still remain very mysterious, unbelievably powerful objects that can consume enormous amounts of matter and effectively remove it entirely from the universe. The gravity remains, basically an echo. But just what is inside the black hole, in the words of Stephen Hawking, is ambiguous and not really part of our reality any longer. But as thought in physics has progressed in black hole science, to this day, strange new possibilities keep arising. And now, there is another one, and it gets very strange indeed. This involves primordial black holes, which are still a hypothetical class of black holes that would have been created in the aftermath of the Big Bang during the inflationary period. They are a legitimate prediction of the physics of what we know about that. These would be among the most ancient objects in the universe and may still be with us, slowly evaporating away, but also may have formed the core of many of the supermassive black holes we see at the heart of galaxies, including the Milky Way. Those supermassive giants may have once started out as very tiny, primordial black holes accreting material. We just don't know. As an aside, interestingly, a supermassive black hole is not the most dangerous type of black hole in the universe. Even for their size, if you fell into the giant event horizon of one, it's thought you wouldn't actually be able to tell that you did, unless you tried to escape it. Otherwise, you would see the universe as you saw it just before you entered. It's the much smaller stellar mass type black holes that are the real monsters, where the scenarios of spaghettification start coming into play. But now we have a new possibility regarding primordial black holes, and it's a weird one. they might be triggering at least some Type 1a supernovae. This story also indirectly involves the idea that primordial black holes may be the answer behind dark matter. The problem is, you need a lot of them for that, as in the vast majority of our universe would need to be made up of primordial black holes. And if that's the case, they vastly outnumber normal stars. In a nutshell, all that excess gravity we see and call dark matter may just be black holes. So here is the weird possibility hidden in here. If primordial black holes are that numerous, at some point across their journey through space, they occasionally, which means often for the universe as a whole, hit a star. And one type of star, actually a stellar remnant, is important here. It's white dwarfs. This is where Type 1a supernovae come in. These mysterious explosions do not have a particularly clear explanation for why they happen. But the usual mechanism is put down to two stars in a system. One a white dwarf accreting material from its companion until enough accumulates to cause a nuclear reaction and the whole thing blows up. But there was an idea that at least some of them might actually be caused by a different mechanism. Interestingly, that mechanism is a primordial black hole punching into the white dwarf. The idea being that this would cause powerful tidal forces rippling through the X star, which might destabilize it and cause it to explode as a Type 1a supernova. Interestingly, a single-member white dwarf system is in store for us in the future. When the sun expands into a red giant, it will then eventually reduce into a cooling white dwarf that could very easily get hit by one of these black holes if this mechanism exists in reality, and providing there are still any primordial black holes left by that time. This would mean that our solar system could basically explode at some point during the white dwarf retirement of the sun, which will persist for many billions of years as the cinder cools. I doubt there will be any humans left here by that point. We will either have gone extinct or moved on into the galaxy to greener pastures. But it is an interesting new possibility because before this, there seemed to be no path to a supernova of any type ever happening here. Now, there seemingly might be, but not just for the sun, but most small stars that end up as white dwarfs. The red dwarfs have this in store for them, and also a strange hypothetical blue dwarf stage that we've never seen. But ultimately, they too should become white dwarfs in the far distant future, regardless of what happens in their evolution. None have had the time to do that. But trillions of years from now, if again primordial black holes have not all evaporated, which by then most of them likely would have, then there is at least a hypothetical means for a red dwarf, or what was formerly one anyway, to generate a kind of violent supernova. Anyway, to test this idea out, a group of scientists at SUNY Polytechnic, the University of Tokyo, and others looked at motion, brightness, and the chemistry of supernovae of this type that could have been generated through this mechanism. The same team in a 2025 paper showed that supernovae generated by primordial black holes are in line with the predictions of the hypothesis as far as properties go. The new study compares the models to known supernovae remnants of this type, specifically in regards to chemical abundances that were predicted. They look particularly at radioactive isotopes of nickel, 56 and 57, in conjunction with stable elements such as stable nickel and manganese. This allowed the team to estimate the mass and chemical composition of the star that generated the supernova and its remnant. They also looked at how such a mechanism might have governed to some degree galactic chemical enrichment, something very relevant to Earth and life on Earth, because it is thought that most of our heavier elements were actually forged in a nearby supernova long ago. Lo and behold, the team found that to explain the chemical abundances of the stars in the Milky Way, a non-zero number of primordial black hole generated Type 1a supernovae appear to be needed. What non-zero means here remains to be constrained, but it does point to the possibility that this mechanism does in fact occur in the Milky Way. By proxy, this also may give us a path to determine whether primordial black holes themselves actually still exist. This is unknown territory because while the physics predicts their formation during the inflationary period, it's unclear if any were left because most of them wouldn't have necessarily been particularly massive. And they are still black holes, So if they do not get fed, they evaporate through Hawking radiation, and there may be not very many of them left, if any. But that depends on how much mass they started out with and other factors, and that leaves it open that they may still be around in great numbers. But since the only thing they emit is their Hawking radiation, which is incredibly weak, as such there could be a primordial black hole sitting in our solar system, and we'd never directly detect it. Oddly, however, remember the question of Planet 9 is still up in the air. The constraints are coming down on that one as far as spotting it as a new 9th planet. Most of the sky is eliminated at this stage, and yet no one has found it. And yet the effects attributed to a gravity source out there somewhere persist. And thus there have been suggestions that if you can't resolve that, and you still don't find a planet, there may be a primordial black hole out there doing it. But the only way we can detect it is by its gravitational perturbations on objects in the outer solar system. Add that with the new potential ability to see the fingerprints of primordial black holes in supernovae and the chemical composition of galaxies, then we step further in establishing that primordial black holes do, or at least did, really exist and are actively engaged in the evolution of the universe, and even the creation of the elements needed for life. There are other types of supernovae and kilonovae that also do that, and of course stars in general with their fusion. But it's interesting, and with a bit of a stretch of luck, we might be able to determine if primordial black holes account for dark matter, one of the greatest mysteries of astronomy. We shall see. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently weathering this year's vegetable apocalypse. The corn is out of hand again as usual, but also lots of tomatoes and chili peppers and herbs, and overall it was a productive year. Even though I will be making spaghetti sauce and salsa until the cow comes home. And since there isn't a cow, yeah, I'm going to be at it for a while, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.